Have you ever considered what allows our electronics to perform complex calculations and operations at such incredible speeds? Transistor switch response time is primarily determined by the time it takes to charge and discharge parasitic capacitances within the transistor itself and its immediate circuit environment. This includes factors such as the transistor's inherent design, its operating conditions, and the characteristics of the external load it is driving. The core reason lies in these unavoidable parasitic capacitances. Imagine them as tiny and scene storage units for electrical charge. Every time a transistor switches, it needs to either fill these capacitors with charge, turning on, or drain them of charge, turning off. This process is not instantaneous. For example, in a field effect transistor, the gate capacitance must be charged and discharged through the gate resistance. Similarly, junction capacitances exist across the transistor's internal semiconductor regions. The speed of this charging and discharging is governed by what engineers call an RC time constant, a product of the resistance and capacitance involved. A smaller RC time constant means faster switching. Several factors influence these critical time constants. The internal geometry of the transistor plays a huge role. Smaller transistors generally have lower parasitic capacitances. The voltage levels and the amount of current available to charge or discharge these capacitances also dictate speed. A stronger drive current can charge or discharge the capacitances more quickly. Furthermore, the semiconductor material's properties, such as carrier mobility, affect how fast charge carriers can move through the device. The external circuit's resistance and capacitance also add to the overall RC time constant, directly impacting the observed switch response. For engineers aiming to optimize switching speed, this understanding is vital. Designers can reduce parasitic capacitances by using advanced fabrication processes that create smaller, more compact transistors. They can also increase the drive current by making the transistor larger or by using higher supply voltages, though this often comes with trade-offs like increased power consumption or larger physical footprint. Another strategy involves minimizing the external resistance and capacitance of the circuit connected to the transistor's output. Sometimes, selecting a different type of transistor altogether, like a specific type of field effect transistor known for high-speed operation, is the most effective approach. Understanding these underlying electrical principles allows for the design of faster, more efficient digital circuits. By carefully managing parasitic capacitances, drive currents, and circuit impedances, engineers can unlock impressive clock speeds and enable the rapid processing that defines our modern technological landscape.